Hello, Trig students. Let's do a lesson on transformations of trig functions. Specifically, how do you describe the transformations that are happening and how do you graph it? First off, we'll start here with our general form. We have four different variables that could affect the graph. Up front, we've got the a value, and that one is controlling our um, vertical stretch and strength, so that would be dilations, and also reflection over well, it would be a vertical reflection, so over the x-axis. So we're looking at vertical dilation and vertical reflection, all of those controlled by the value of a. Then we have in here a b value, and this one is inside the parent function, which means when it's happening before the parent function occurs, that's controlling horizontal transformations. And so we have b here would be the horizontal dilation. And if it's negative, that would also be the horizontal reflection. So reflection over the y-axis. Okay, then we have a C value. This is what's going to control the horizontal translation. Okay, so side to side movement. And remember that it says minus C here because this one moves opposite of what you would think it should do. So this would be horizontal translation, opposite of what it looks like. And then finally, we have the D value, and this one is vertical translation, so up or down. Okay, and this one says plus d. Vertical moves exactly like you think it would. So just like when we were studying other functions beside trig functions, anything that's working horizontally works opposite of how you think it should. So putting a number 3 out front, for instance, you might think that that's going to make it bigger by times 3, but it's actually going to shrink it by a factor of 3. Um, when you see a minus a number inside the parentheses with x, if it says minus something, it's actually moving it not in the negative direction, but in the positive direction. So there's our general form. And let's specifically look at a transformation of the sine of x. So we start out with our parent function, f of x equals sine of x. And then what we're going to do is have x plus pi divided by 2, all of that quantity inside the sine, and then a plus 1 sitting around out back. Let's see what that does to the properties of the parent function. All right, we're going to begin with describing what's happening here. So I see this pi, and it's plus, and it's inside the parenthesis. And so that's telling me it's like in the C spot right now. And this says plus pi, which means we're going to move horizontal translation pi to the left, because it should be opposite of what we would expect. Now, I've got this divide by 2 in here, and you might be saying, well, there's no divide by 2 up above. But think about how this is equivalent to what we see up above. Dividing this whole statement right here, x plus pi divided by 2, would be like having a 1/2 out front in this b spot. So we're really multiplying that whole inner expression by 1/2. And that means that the b value is 1/2. This would mean it's a horizontal dilation. And specifically, since we're multiplying by 1/2, you might think, oh yeah, 1/2 means get smaller. But horizontal ones work opposite of what you would think. So it's really a stretch by a factor of 2. Okay, and so that's what this 2 does right down here. Should have thought this through better. That's all right. I'll just cross my arrows. And then finally, we've got this 1 plus 1, and that's outside the parentheses. That's like the D out here. And so that's telling we're going vertically. Translation. And that would be up 1 unit. And remember that the verticals behave just like you think they would. So plus 1 really does move it 1 unit up. Okay, so what's this going to do to the graph? First off, let's talk about one of the properties of a graph, which is the period. Period meaning how far do you have to travel in the x direction? What portion of the domain do you need to see the full picture of the graph, the full cycle of the graph? And then we have learned that in this case, the period of the parent function, the period of sine of x, is just 2 pi. Okay, well, what is the period then of the child? Okay, and again, the child in this case is this g of x. And that would mean that we're going to take what the parent function was before, and we're going to multiply it by a value to change to the period of the child function. And up here, we got done saying that the horizontal dilation is a stretch by a factor of 2, which means that it used to be 2 pi as our period. Well, now that 2 pi is going to get stretched out. It's going to increase the distance away from the y-axis by a factor of 2. So I'm going to multiply it by 2 and get a period of 4 pi. There we go. Okay, so the period of g of x is 4 pi. It's been stretched out. Okay, do note that, yes, we said that it was dividing by 1/2, or sorry, multiplying by 1/2 up here, but we didn't multiply the period by 1/2. We multiplied it by 2 because that horizontal dilation made it go opposite of what you would expect it to do. It got wider by a factor of 2. Okay, let's keep going. We've got the period done. Now let's talk about something called the initial interval. So if you look back at the original function of sine of x, if you look at that sine of x, this is related to the period, but we haven't really talked about this specific vocabulary before in class. The idea that where's the quote unquote main portion of the graph? What could you where would you draw to get the main period of the graph shown? And so this idea for the parent function for sine of x, that happens between 0 and 2 pi. If you graph all the x values between 0 and 2 pi, then you'll get a full picture of what the full cycle of the graph looks like. And again, that's related to the period. The period was 2 pi, so if you go from 0 to 2 pi, that's the full initial interval. And I said less than, like x is between 0 and 2 pi, but it actually could be equal to as well because it's not limited. We don't have any limitations on the domain of x, or sorry, the domain of the sine. Now, what do you do with that initial interval when you want to talk about the child? There's a really nice little technique that you can use, and that would be that we're going to rewrite this initial interval that we had for the parent function. So that's 0 and 2 pi. But instead of putting just plain old x in the middle, I'm going to go back to our equation up here and write the expression that was being that the sine was being applied to. There we go. So down here, I'm going to write x plus pi divided by 2 and fill that in for this initial interval. Now what this is going to do is tell us where the initial interval of sine, so sine is originally from 0 to 2 pi, where that's going to end up after this transformation happens. So I'm going to solve for x. And if this worries you that we've got two inequality signs in here, that it's a compound inequality, just keep in mind that I'm really solving two inequalities at the same time. I'm solving this one and I'm solving this one. And just to save time, I'll do both of them at the same time. So I see right here, how do I solve for x? I've got x plus pi divided by 2. First, I should get rid of divided by 2, which means I should times by 2 on both sides, or in this case, all three sides. And let's see what's going to happen. 0 times 2 is still 0. This part right here, this divided by 2 and times by 2 is going to cancel each other out. And I'll be left with x plus pi in the center. And then 2 times 2 pi is 4 pi. Okay. Now, if I look at this next part, I want to get x by itself, so I'll subtract a pi. Okay, we end up with negative pi is less than or equal to x is less than or equal to 3 pi. Okay, so what does that actually tell us? Okay, well, let's look back up at the graph for a minute. If I graph my parent function, the sine of x, remember that the sine of x passes through 0, 0. It reaches its max up here. It passes back through 0 here, goes down below, and we have an amplitude of 1. So the parent function would look something like this on its initial interval. Now, when I look at this new interval, it says the initial interval for the child function is from negative pi to 3 pi. Well, okay, I can see that the distance between negative pi and 3 pi is 1, 2, 3, 4 pi's, which makes sense because over here we said that the child function is going to have a period of 4 pi. That's the entire distance you need to go to see a full cycle. And the reason that it ends up from negative pi to 3 pi is because we not only stretched it, but we also moved the entire graph. Oops. We moved the entire graph pi units to the left. So that's why it ends up stretching and then sliding over here. So our starting point for our graph that we're going to have here for the child function would be back here at negative pi instead. Okay, let's go ahead and graph that. Now I realize I do have one more thing left to go. I still have that +1. We haven't tackled that guy yet. But let me draw an intermediate graph. So before putting the +1 on there, what this would look like is that this point is now over here at negative pi. The other end is over here at 3 pi. Okay, so that's the ends of an interval. The maximum height, we didn't do anything to change the vertical position or the vertical dilation at all. And so what I'm looking at here is that I should still be at a height of 1 and negative 1. Halfway between is still going to be here at pi. And then the peak of this part will be halfway between the center point and the end of the interval. So this point right here is going to be over here at +1. And this point will be halfway between these guys down here at -1. Okay, so if I kind of trace this in a little bit lightly, what you should see is a much stretched out version of that sine graph. So it's twice as wide as it was before, and it's been slid pi units to the left. Okay, now though, we do want to finish this graph. And the final thing I have to do is do the vertical translation up 1 unit. So that means that wherever anybody is at on my pink intermediate graph right here, now I need to move all of those points up 1 unit. And this is a +1. This is not timesing by anything. So that means nobody's going to stay put like it would be if it was a dilation. It means that all of our points, let me see if I can grab a new color. All of our points are moving 1 unit up. So we've got 1 unit up, 1 unit up, 1 unit up. Okay, so up here is where g of x is going to belong. 1 unit up from where that pink graph was at. Oh gosh. There we go. Pretend that looks nice and smooth. There we go. This orange graph right here is g of x. So we have the dashed blue one was the parent, that's f of x. The pink one was an intermediate step, and then finally we end up over here at g of x. Now, of course, you know that sine functions like this continue to go on. Like it's not like this graph just ends right here at 3 pi and at negative pi. But what we're saying is we're trying to show where that initial interval ended up so that you can really get a picture of what this final graph looks like. You can have some perspective. on how it compares to what the original was. Now there's a few more things that you can say, a few more properties you can identify about the graph of g of x. G of x, we could say, what is the amplitude? Whoops, it would help if I could spell. Okay, amplitude is half of the highest point minus the lowest point. But remember a second ago, we said we didn't change the amplitude at all. And so the amplitude is still 1, just like it was originally for the parent function. What else do we have? We have amplitude. We have oh, did we have any reflection? Nope, no reflection. What else could we talk about for this graph? Oh yeah, did we have any phase shift? Well, yes, we did. That's just another way to describe what's happening with the horizontal translation. So phase shift is a specific vocabulary for a horizontal translation for trigonometric functions. So we had pi to the left. So pi, and I'll actually just write pi to the left, like that is the phase shift. That's what happened with this graph. It's movement in the horizontal direction. What else can we talk about? Domain. Okay, we know that the domain is not limited for the sine, so the domain is all real numbers. And what is the range? Okay, well, range would be the lowest to the highest point on our graph. And so looking at our orange graph right here, the lowest point is at 0. The highest point is at 2. And I know that those can be included. I don't know why I wrote them so far apart. I guess I was getting ready to write an inequality, but interval notation is nice. So from 0 to 2 inclusive, all those points from 0 to 2, including those endpoints as well. All right, I'll also do a example with a tangent function, but I think that'll be in a separate video. All right, hope you enjoyed. If you got questions, send me some emails.